Okay, welcome to iLecture Online, and here's another interesting example of how to deal with resistors in parallel and series. On top of that, you're also supposed to find the current in each resistor and also the voltage drop across each resistor. Now, before you know how to find the current and the voltage drop in each resistor, you first have to take this circuit and reduce it into its simplest form. In other words, find a single resistor that could replace all of these resistors. Find the total, or what we call equivalent resistance. And how do you do that? Well, the first thing you do is find a way to simplify it as much as possible. For example, you could take these two resistors here and combine them into a single resistor. So let's go ahead and start with that. Take the 2 ohm, they're in parallel. So you can say that R1 and 2 is equal to the product, R1, R2 over the sum, R1 plus R2. And that would be 2 times 2 divided by 2 plus 2. So that would be 4 divided by 4, which is 1 ohm. All right, so I can replace those two by a single 1 ohm resistor. So the circuit can be redrawn to look like this. So these two resistors now will become a single resistor, and I still have those resistors right here. So right there, and right there, like so, and I'm back to the battery. Now, I'm going to leave off the ohm symbol everywhere. So you can say that this is now, maybe not. So this is 1 ohm resistor right there. And here is still R3, R4, and R5. And this is a 4 ohm resistor, this is a 4 ohm resistor, and this is a 4 ohm resistor. So it looks a little cleaner that way because I'm running out of room. Okay, next step. I'm going to combine these two resistors. Now those are in series, so I can simply add them together. 4 plus 4 is 8. So we can say that R3 comma 4 is simply R3 plus R4, which is equal to 4 plus 4, which is 8 ohms. So these two resistors can be replaced by a single 8 ohm resistor. So that's equal to, or the new circuit is, okay, here's the 1 ohm resistor. There, now that becomes a single resistor. There's a single resistor like so. Okay, here this is a 1 ohm resistor. Now these two combined become an 8 ohm resistor, and this is still a 4 ohm resistor. All right, now I'm going to combine these two, and of course I'm going to use the product over the sum. So the product would be 8 times 4 over the sum, which is 8 plus 4, which is 32 divided by 12, which is 16 divided by 6, which is 8 divided by 3, which is 2.33. Let's see if I did that right. 32 divided by 12, so the product over the sum, that is 32 over 12, that's 16 over 6, that's 8 over 3. Yeah, oh, nope, that's not correct. I thought something was not right here. How about 2.67? It didn't seem quite enough, so something wasn't right. I just want to make sure I got that right. All right, I can now redraw the circuit. Now it looks like this. So we have one resistor here, and we have another resistor here. So this is a 1 ohm resistor, and this now becomes a 2.67 ohm resistor. And now, of course, those two are now in series. You can combine them into a single resistor, adding them up. So we have 1 plus 2.67, which is 3.67. And so this becomes a circuit with just a single resistor, like so. Now, did I give you, I need to give you a battery value here. How about a 10-volt battery? So V equals 10 volts, V equals 10 volts, V equals 10 volts, V equals 10 volts, and V equals 10 volts, and R total is a 3.67 ohm resistor. So it had a single 3.67 ohm resistor. It could replace all these resistors, and you get the exact same effect in the circuit with the exact same amount of current. So now that I have the equivalent or total resistance, I can say that I total is equal to V divided by R total, which is equal to 10 volts divided by 3.67 amps. Oh, no, not amps, ohms. I'm not at the amps yet, because that's the final solution. And what's 10 divided by 3.67? It's 2.72. So 2.72 amps is the total or equivalent current running through the circuit. So we can say here that we have an I total equal to 2.72 amps. Now I'm supposed to find the current in each of the 5 resistors. Now notice, when the current comes around a corner here, it has an option. It can go in the top branch or the bottom branch. And notice that the 2 resistors are the same. So since the current sees an equal amount of resistance in the 2 branches, the current will split evenly into the 2 branches, which means that each branch will carry half the current. So that means that I through R1 is equal to 1/2 I total, which is equal to half of that, which is 1.36 amps. And I through the second resistor is equal to 1/2 times I total. And so that will also be 1.36 amps. Notice that when you add the 2 together, you get back to your total current. So then the current will recombine into the total current to this part of the branch right there. So you'll back up to 2.72 amps here, and then the current will redistribute itself between those 2 branches. Now notice that this top branch has an equivalent resistance of 8 ohms, and the bottom branch has an equivalent resistance of 4 ohms. So really what we can do is look over here and say, okay, at the top branch, the current will encounter 8 ohms of resistance. In the bottom branch, the current will encounter a 4 ohm resistance. So more the current will go through here, less current will go through there. And since this is half the resistance of this resistor, it will get twice as much current as this one. So this one will get 2/3 the current coming from here. This one will get 1/3 the current coming from there. But again, if you want to make sure you know how to do that, you can say that I through the bottom branch, so I R5 is equal to I total coming in times the ratio of the resistance in the other branch, that would be R34, divided by the total resistance, which is R34 plus R5. And so this would be equal to I total, which is, well, let me actually put the values in. So I total is the 2.72 amps times the ratio of the resistance 3,4, the equivalent resistance is 8 ohms, divided by 8 plus 4. Oop, that's not a very good 8. So that would be 8 plus 4, which is 2/3 of 2.72 amps. So divided by 3 times 2 equals, that would be 1.82 amps. 1.82 amps. And to find the resistance through the R5 resistor, oh, no, that's what I just found. To find the resistance through the top branch, so I through the top branch, which is R34, is equal to I total times the ratio of the resistance in the other branch, which would be R5 divided by R34 plus R5, which is equal to 2.72 amps times 4 over 8 plus 4, because R5 is 4 ohms, and that would be 1/3 of that, which would be equal to 0.90 amps. So there's a slight little round-off error, but we're good with that. All right. So now we know the current in each of the resistors. We know that we have 1.36 amps going through R1. We have the same amount going through R2. We have 1.82 going through R5, and we have 0.9 amps going through R3 and R4. So we now have the currents through the 5 resistors in our problem. Now we still need to find the voltage drop across each. What's the voltage across each of these resistors? So this one, this one, this one, this one, this one. Okay, to find the voltage drop, voltage across resistor 1 is equal to I through resistor 1 times the resistance R. So I times R gives us the voltage drop. That comes from Ohm's law, where the current is equal to V divided by R. So rearranging that so we solve for V, we get I times R. So for R1, I is 1.36 amps, and the resistance is 2 ohms. So that would be equal to 1.36 amps times 2 ohms. And so that would be equal to, let's see here, 2.72 volts. And of course, we get the same for R2 because it's the same resistance. IR2 times R2, which is equal to 1.36 amps times 2 ohms, which is equal to 2.72 volts. So we have 2.72 volts across this resistor and 2.72 volts across this resistor. So now how much do we have across each of those? So looking for R5, V across R5 is equal to I through R5 times R5. And the current through R5 is 1.82 amps, 1.82 amps. Multiply that times 5 ohms, and that would be equal to 5, that's 5. That's, 1.82, 10 volts. Something doesn't seem to add up. Let me check this real quick here. 1.82, 2.72 divided by 3 times 2 equals 1.82. That's about right. Multiply times 5 equals 9.01. That doesn't seem right. 9.01 volts. The reason why that doesn't seem right is because those two added together should add up to 10 volts, and it adds up to more than 10 volts, so I know there's something wrong. So I just noticed an error. I noticed that I put 4 ohms down for R5 instead of 4 ohms. So 4 ohms instead, which gives us a different value for the voltage drop across R5. So we get 1.82 times 4, which is 7.28 volts. And that makes sense because the two added together, remember the voltage drop across here plus the voltage drop across there must add up to the voltage of the battery. So 7.28 plus 2.72 does add up to 10 volts. And the voltage across the branches must be the same as well, which means that the voltage drop across R34, the two resistors combined, is I through R34 times R34, and that should of course be the same. So that should also be 7.28 volts because we know that the voltage drop across branches must be the same. But now the voltage drop is divided between those two resistors and they're the same in size. That means half the voltage will be dropped across this one and half the voltage will be dropped across this one. So we can say that the voltage across R3 is equal to half of 7.28 volts. So half of that is 3.64 volts. And of course, the voltage across R4, which will be half of 7.28 volts, which is also 3.64 volts. So now we have all the voltage drops across all the resistors. We have across each one of these two a voltage drop of 2.72 volts. Across this one, a voltage drop of 7.28, and then each of those will take half of that voltage drop, 3.64 and 3.64. So now we have the currents through each of the resistors and the voltage drops across each of the resistors. And again, to recap, because this is kind of a complicated problem, you're given a resistor circuit with resistors in parallel and in series. You then first find the equivalent resistance by slowly reducing resistors a few at a time until you're down to the equivalent or total resistance of the whole circuit. From that, you can find the total current. Once you have the total current, you then see how it branches out and use the technique that we've learned here, or realizing that if the resistors are the same, then the current will simply be split in half through each of the two branches. You find the currents through each resistor, and then to find the voltage drop across each resistor, you simply multiply the current through the resistor times the resistance itself, and it'll give you all of the voltage drops or the voltages across each of the resistors. So that's how you do one of those resistors in series and parallel problems.